you are, please type yes in chat. So I think those of you who have been here for more than 4 days now should really be recognized. And it's during the pandemic COVID situation, it's really pity that we cannot do it in person. However, for those of you who type yes, if you meet me in person in the future, I hope very soon, please let me know and I will buy you a coffee, okay? So let me share my screen and let's get started. Okay, so to make sure we have the best quality of the audio, I'm going to turn off my video, okay? I don't think you will miss much, right? So, all right. Today is day 5, and today, in these 3 hours, I'm going to talk about something related to hydrologic modeling and specifically application to urban hydrology. Okay, so the title is Urban Hydrology and Hydrologic Modeling, Remote Sensing Application in Urban Hydrological Modeling. Okay, so let's see. Okay. So first, I'd like to introduce myself. My name is Zhenduo Zhu, in Chinese, Zhu Zhenduo. I got my bachelor's degree from Tsinghua University in 2009 in hydraulic engineering. Then I continued my master, PhD, and postdoc all at the University of Illinois at Urbana-Champaign from 2009 to 2016. Then since 2016, I'm assistant professor at the University at Buffalo, the State University of New York. So my research focused on hydrologic and water quality modeling, especially across multiple scales. So as you can see here in our group, we work on as large as a nation scale to a large watershed scale, and also zoom into urban river or urban system scale. Okay, so this is my research background. And for this summer school, I want to share with you something about urban hydrology and hydrologic modeling. So it is my understanding that for this summer school, I want to provide basic content. So this is not like cutting edge research. I do want to share a little bit of cutting edge research during the presentation, but most of the time, this is quite basic. So if you have already taken classes in remote sensing or hydrologic modeling, I apologize, you may not learn too much more from here, but hopefully some of the stories I want to share with you, hopefully they are useful, okay? So the outline of today's class, I basically divided into 4 chapters or 4 parts. In the first part, I want to introduce a brief history of urban hydrology. In part 2 or chapter 2, I want to talk about hydrologic principles and how remote sensing can help to understand hydrology. Then in part 3, I will talk about urban hydrologic modeling using SWIM. And in part 4, we will see some SWIM example and application. Okay, as you can see here, between 2 parts, there will be short breaks and a little long break. So just hopefully, if I can finish earlier than the schedule, maybe we will have more break, or maybe I can have time for some questions. So yeah, just hope I will not be late. Okay, let's get started with chapter 1. Okay, a brief history of urban hydrology. So Before urban hydrology, I think first, obviously, we should talk about hydrology, right? Hydrology, this word comes from ancient Greek. Hydro means water. Logy means the study of. So basically, hydrology means the study of water, right? And as you can imagine, like urban hydrology means the study of urban water, right? So hydrology deals with occurrence, circulation, storage, and distribution of surface and groundwater on Earth, and their chemical and physical properties, and their interaction with the environment. Okay. So water management is really one of the oldest professions in the world, if not the oldest, for sure one of the oldest professions. Because humans need water, right? So water and food are essential to human beings. And in order to grow food or obtain food from animals, we also need water, right? So it makes totally sense that from the very beginning that people try to settle down close to rivers where you can get water supplies, right? So here are some examples. If you look at the early civilizations, okay, so all of these early great civilizations grew up in river valleys. Okay, so those are the Yellow River, the Yangtze River civilization, the Indus River civilization, the Tigris, Euphrates River, and the Nile River civilizations. Right. So I'd like to go through one by one to introduce what humans were doing back then regarding urban hydrology. Okay, I'm not sure we can call it urban or not, but some of the concepts are pretty similar to what we call like modern urban hydrology. Okay, so water supply, stormwater, and the sewage drainage, they are basically, the most important problems, especially water management problems for human settlement, right? So as you can imagine that when humans started to settle, right, and live together, okay, so one of the most important thing to consider is where to get water, and then where to dispose wastewater, and where to dispose sewage, right? So this is an example actually excavated very recently. If I remember correctly, this is early 2020, so just before the pandemic. Okay, in Henan province in China, called Pingliangtai, so which belongs to the Longshan culture. This is located in the lower Yellow River. About 3000 to 2000 BCE, right, which is more than 4000 or 5000 years ago. Okay? So here, from the excavations, people found out that back then, right, human already started to use drain pipes, okay, which are connected with drainage ditches, right, and the pipe is made of pottery, tao. Okay? So this is believed to be China's earliest and most complete urban drainage system, and also one of the earliest in the world. Okay. So here is a recovered complete pottery drain pipe, but as you can see, is mostly broken right now. Okay. So the other example of how humans use water, especially for settlement, is the Liangzhu culture, which is located in the lower Yangtze River, also about 3000 to 2000 BCE, right? The same, similar as the Longshan culture. So here in Liangzhu culture, people have discovered there is a city. So of course, not comparable in terms of scale and size, population to like our cities now, but back then is pretty impressive, right? And more impressively, people started to build dams to first protect from flooding and also to get water supply into this city. Okay, so just think about that 4,000 or 5,000 years ago. Okay, so here is another example in the Indus River civilization, Harappan culture. So this is a city called Mohenjo-daro. I hope I pronounce it close. Okay. So here, similarly, people have found that even at more than 4,000 years ago, so humans started to know like how to drain stormwater as well as wastewater from their settlement into rivers. Okay, so in this case, it would be the Indus River. Okay. And also, as you can see here, so back then, people already started to have a bathing room and also knows how to drain the water from the bathing platform, into a surface channel, right? And then finally goes to the river nearby. Okay. So here again, we are looking at about 3,000 to 2,000 BCE, located in the Tigris-Euphrates River. So what's a city called Tel Asmar, or also called as Ashunana. Again, sorry if I pronounce it wrong. Okay. So this belongs to the Mesopotamia culture, and here, as you can see, in this northern palace, there has been drainage system highlighted in blue in this figure. Okay. This is how it looks like now. So as you can see, there is drainage channel that is lower than the street, which is covered by bricks, right? And also people found the outfall pipe, right, which drain into street. Okay. So if we look at the last one, the Nile River civilization, here in the pyramid of Sahur, again back to 4,000, more than 4,000 years ago. So people started to use copper pipe. So instead of pottery or clay. Okay. So obviously this is more advanced material, and this back then they cannot use it throughout the whole drainage system, but only like couple hundred meters. However, I think it's already very impressive. Okay. So also I want to point out this is not urban drainage or water supply, but a very impressive invention, which is called nilometers. Right? This is in ancient Egypt at the Nile River more than 5,000 years ago. People started to measure the water level of the Nile River. Because the agriculture in ancient Egypt heavily depends on the flooding of Nile River, which delivers nutrients to the soil, to the land. Right? So if you know the water level, you can actually predict the agriculture production for the coming season. Okay? So just think unbelievable that how like 5,000 years ago, people started to collect those knowledge. Okay. So given what we have said about the impressive projects or drainage systems or materials, okay. However, in terms of hydrology from a scientific perspective, this oldest profession actually took a long journey to reach our modern understanding about hydrology. Okay, so I would just ask you to imagine if there is a time machine that you can actually travel back to 4,000 or 5,000 years ago, right? Even with the knowledge you have, okay, how are you going to convince human back then what hydrology should be, right? So for example, like what hydrologic cycle should be. Where does water in rivers come from? How does water get up to the mountains? Why doesn't a river flow reach the level of the sea? Okay. So those may seem very simple questions for now, but back then, those are very, very challenging. Okay. So the ancient philosophers actually did not quite understand the basic hydrologic principles, such as conservation of mass, evaporation, and precipitation, especially infiltration and groundwater. Okay? Those are very, very challenging for ancient thinkers and philosophers. Okay? So if you go back to ancient Greece, right? If you can sit down with Aristotle and ask Aristotle those questions, he probably wouldn't be able to give you an answer, or at least not the correct answer. Okay? So because of that, there are hypotheses. People have proposed. Okay. So one very interesting hypothesis, which actually was pretty widely accepted, at least in ancient Greece, is the underground reservoir hypothesis. Okay, so they believe that water is pushed up to the mountains by some kind of source. Okay, some kind of a force, maybe vacuum force, or capillary action, or rock pressure, whatever. But those water are actually pushed up to the mountains from underground reservoirs. Okay? And these underground reservoirs were replenished by the ocean. Okay, I think it sounds very interesting for us now, but again, like this hypothesis was widely accepted for a very, very long time. Okay. Then in the first century, Vitruvius, a Roman, so he actually wrote down that the mountains received precipitation that give rise to stream flow. Okay, so this has been a big step forward, right? So at least he answered the question, where does water come from in river correctly? Okay, so his answer is the mountains receive precipitation, and then the precipitation actually cause stream flow. Okay. Also, at the same time, he acknowledged a filtration process. So he noted that water can percolate into soil, and he called it filtration. Okay. So at about similar time in China, 吕氏春秋, Huan Dao. Huan means yuan, basically circle. So that is about 239 BCE. So it was recorded that 海水上升为云, meaning that water in the ocean can become cloud, right? And then the cloud will move to the west. That is because if you know the geography of China, so China actually the ocean is located on the east side of China, right? So that's why he said the cloud will go once formed on top of the ocean, it will go west. Okay. And then the rivers will flow east into the ocean. Okay, so later in about Han Dynasty, Gao Yu in 吕氏春秋注 and 淮南子注 which is about 150 to 220. So he has explicitly noted a circle that goes from ocean to cloud, then to rainfall, then the rainfall goes to the river, and then river goes back to the ocean. Right? At the same time, he also noted some circle about groundwater, but again, the infiltration concept is not clear, at least not recorded explicitly or clearly back then. Okay, so basically, now if we do a very quick summary, if you think about from 5,000, 4,000 years ago until about 2,000 years ago, it took about 2 to 3,000 years for human beings to kind of get the hydrologic cycle correctly. Okay, so still is not very complete. It's not quantitatively proved, but at least we get this most of the circle correctly. Okay. Also, about the same time, hydrologic engineering had been advanced a lot, right? I'm only showing you one example, which is the Roman aqueducts. So this is in the 1st century. So here in the picture, we are showing part of a 50-kilometer aqueduct. And what is more impressive is the gradient of these aqueducts is only 1 in more than 18,000. Okay. So which means back then, people must have mastered the technology of measuring elevation very well. Okay. Okay. So this is kind of a very brief history from 3000 BCE until like the 1st century. Okay. Then unfortunately, from 1st century until 16th or 17th century, there's not much things like too exciting. Okay. Well, I shouldn't. Okay. I should take it back. So there are a lot of engineering practices which are very, very impressive. For example, in China, we have Dujiangyan, right, which still functions now. But in terms of hydrology, in a scientific perspective, it didn't go very far. So interestingly, it is until the 17th century, in 1600s, that people started to make measurement and try to prove the hypothesis which had been proposed a long time ago. Okay, so one of the first measurement was done by Pierre Perrault. So he documented his measurement in this book called On the Origin of Springs. And he basically tried to prove that precipitation could account for stream flow in the Seine River in France. Okay, so what he did, he measured precipitation near Paris for about 3 years. He estimated discharge of the Seine River. Oh, by the way, one, I think, important reason why from the 1st century until 1600s, there were not too much advancement in terms of the science. I think one important reason is because the measurement technique. Okay, so you need a very good measurement technique in order to do this kind of study, right? And that later I will talk about the remote sensing technology. So obviously, that wasn't there back then. Okay, so then after measuring precipitation and measuring flow discharge, so he multiplied precipitation by the drainage basin area and found that the volume of the precipitation was actually 6 times the flow discharge. Okay, so at least quantitatively, this is the first proof that precipitation is large enough, right? The amount of precipitation or the volume of precipitation is large enough to account for stream flow. Okay. So later, this same conclusion was supported by similar experiments, but with better measurement techniques. For example, one of that is Marriott. Okay. So I'd like to point out that those are very, pioneering scientific research. Okay? However, due to the limitation of the measurement and also the limitation of a lot of other knowledge, right? So as you can see here, this is not a very complete water balance analysis, right? So it is simply precipitation versus stream flow, right? So he did not discuss about infiltration or other processes in the hydrologic cycle or in the in the whole entire water balance. So later, by the end of 1600s, Edmund Halley used a small pan to estimate evaporation from the Mediterranean Sea. Then from his study, he demonstrated that the evaporation of seawater, basically the Mediterranean Sea water, was sufficient to account for observed precipitation in the Mediterranean Sea basin. Okay. So as you can see here, this is the map for the Mediterranean Sea. So Mediterranean Sea is almost closed ocean or water body, right? So in his study, again, it's very pioneer, and I think it should get a lot of acknowledgement. But from a modern perspective, this again water balance isn't really accurate, right? Because as we know now, evaporation actually is a global scale process, right? So you cannot just look at one watershed or one basin, even though Mediterranean Sea basin is quite big, but it is not accurate to only compare the evaporation of Mediterranean Sea versus the precipitation of on the Mediterranean Sea basin, right? So this is precipitation and evaporation should be a global scale process. So as you can see here, right? But of course, back then, there is just no way to do that. And nowadays we can do it largely thanks to remote sensing technology. So after thousands of years, now we have a complete understanding of hydrologic cycle, right? So water in the ocean or lakes, basically surface water can evaporate. Then by condensation, it became the cloud, and by global circulation, this can bring precipitation on the land, right, or snow, right? It could be rainfall, either rainfall or snow, and then the precipitation generate runoff, runoff forms rivers and streams, then finally stream goes back to the ocean. Also, at the same time, precipitation can infiltrate to the soil and became groundwater, and groundwater also from a global scale, it flows into the ocean. Right? So this is our current understanding of hydrologic cycle. So later, in the 1700s and 1800s, so there are, significant advancement. For example, Henry Pitot invented the Pitot tube for measuring fluid flow velocity, which is still widely used nowadays. Right? It was later modified to the modern form by Henry Darcy. And there are also advances, significant advances in hydraulics and groundwater, so both groundwater and surface water by Bernoulli, Chasey, Darcy, Manning, and many others. Okay, so I believe if you have studied hydrology or hydraulics, those names are all very familiar, right? So, however, it is until the early 1900s when the modern hydrology started to evolve. So this start with Sherman, 1932, who proposed the unit hydrograph theory or unit hydrograph concept. Then similar time, Houghton introduced the infiltration formula, and Peirce, 1935, introduced a non-equilibrium method. Then all of this in early 1900s initiated a more theoretical and quantitative approach to study hydrology. Okay. So through the same time, if you look at globally, so it's global urbanization going on, and we have to obviously deal with the impacts of urbanization. So if we compare these two conditions, on the left-hand side, a natural condition, and on the right-hand side, a developed condition. So under the same amount of rainfall, okay? So in a natural condition, we have roughly 40% of the precipitation will evaporate or transpirate, and 50% or half of the precipitation will infiltrate. Right? Then there's only about 10% runoff generated. However, under the same rainfall amount, if you look at a developed condition, okay, because of the land becomes much more impervious in a developed condition than the natural condition. So there will be much less infiltration. So instead of 50%, it's only 15% of infiltration. And also evaporation or transpiration becomes slightly less or 10% less. Then in the end, there will be more runoff. Right? So 55% of the precipitation can become runoff compared to only 10%. Okay? So that's a problem in an urban environment. So this stormwater runoff, this 55% or 5 times more runoff is going to generate problems like this. So like street flooding, basement flooding, and it is still happening right now. Right? So this is from the quantity perspective. So how to deal with that? Again, we have to drain stormwater to somewhere. Right? So this is the same concept as human did back to 4,000, 5,000 years ago, right? So when it rains, we need to drain stormwater somewhere. So we started to build a drainage system. So obviously we have better technology than 4,000, 5,000 years ago. So we can build the underground drainage pipe network that will drain the stormwater runoff as well as the sanitary from the urban environment go to surface water such as rivers and lakes, right? And the idea was to drain it as soon as possible, right? So then we will not have flooding issue. So for a very long time, the focus was on how to engineer solutions to move rainwater rapidly away from urban areas to avoid damages. Okay. However, now there has been new philosophy developing that treat rainwater more valuable as a resource instead of as a hazard or disaster that needs to be moved away, right? So that's the quantity part of stormwater runoff. The stormwater runoff does not only cause quantity problem such as flooding, but also quality problems. As you can imagine, there are all different kinds of contaminants or pollutants that are built up on the parking lot, the street, or in maybe also soil, right? And then when it rains, so those contaminants are going to be carried out by the stormwater runoff. And finally, if you drain it directly to surface water, it's going to pollute surface water, right? So there are all kinds of pollutants there, as you can imagine. So by the 1850s, just as an example, maybe one of the famous examples, in London, more than 400,000 tons per day of sewage were flushed into the Thames River. Okay. So here on the left, there is a cartoon published in 1858, which is describing what is now called the Great Stink. It's because in that summer there is a great stink of waste in the Thames River, right? And which became a public issue, got a lot of public attentions, and finally people started to think about solutions or different approaches. Right? So one of the most important approaches is actually the development of wastewater treatment plants. Right? So that is from the end of 1800s to 1900s. So there have been wastewater treatment plants developed. So here is one example, one of the largest wastewater treatment plants in Chicago. Again, this is taken from an aircraft, actually, again, remote sensing, right? So with the development of wastewater treatment plant, then what happened is instead of drain stormwater and sanitary directly into surface water, now we first drain it to wastewater treatment plant. And then after treatment, the treated wastewater then will be discharged back to surface water, right? So obviously the treated wastewater is much better than the untreated wastewater. So at the time, there are two approaches people considered. Right? One is this here called combined sewer system. Basically, the stormwater runoff and the sanitary sewer goes to the same pipe, right? And then this pipe from what's called interceptor goes into a wastewater treatment plant, and then the treated wastewater goes back to surface water, right? There is an obvious drawback of this design, right? That is because under dry weather, everything is fine, right? Well, if the system works perfectly, everything is fine. The sanitary sewer can be discharged into wastewater treatment plant, then got treated. However, when it rains, right, the combined stormwater and sanitary, the flow can easily exceed the capacity of this combined sewer system. And in order to prevent basement flood or street flood, we still have to let the overflow during wet weather event go into surface water, right? So again, this is not the only solution or approach people considered. Even by the end of 1800 or early 1900, people actually discussed whether we should make it a combined sewer or we should separate them. Right? So we should have two separate sewer systems, one for stormwater only and the other for sanitary only. Right? So people actually discussed these two approaches. And back then, many cities, their managers, after discussion, decided to follow a combined sewer system approach because first, it is cheaper, and second, people believed that this overflow, so basically what we call combined sewer overflow now, would not cause a significant environmental problem. People believed so. Of course, now it is proved to be wrong, but it is always interesting to look back into the history and see how people made decisions based on a different understanding of the values of the environment and also the ecosystem, right? So as I have introduced, then the other approach would be the separate sewer system approach. So basically two separate sewer systems, one for stormwater, one for sanitary. Okay. And most of the newer cities have adopted the separate systems after realizing the environmental problems caused by combined sewer overflows. Okay. However, it doesn't mean separate sewer system doesn't have environmental problem. So often sanitary sewer can still overflow. And in many cities, as I'm aware of, there are construction problems which basically, displace the sanitary sewer and storm sewer wrong. So there are still a lot of issues with separate sewer system, but overall, it is better than the combined sewer system. Right? So then, if you look at this number of a population since 1950, right? So globally, we are facing a growing population problem and a growing urbanization problem. So by 2008, the urban population and the rural population on the Earth reached the same. And after 2008, urban population has continued to increase while the rural population has reached the maximum and started to decrease, right? And by the United Nations, it is estimated or predicted that by 2050, more than 70% of the total population will live in urban environment rather than rural environment. And here is a report from United Nations 2014. As you can see here, the size of the circles represent the city population, and the color represent the growth rate. So except Europe, Northeast United States, and some other places, most of other places are facing a pretty fast growth rate. Right? So from 3 to 5%, in Africa, right, in cities, China, India, and also there are more cities that has a 1 to 3% growth rate. Okay. So in the same report, United Nations says, okay, coping with the growing needs of water and sanitation services within cities is one of the most pressing issues of this century. And sustainable, efficient, and equitable urban water management has never been as important as in today's world. So why do we need to talk about that? So first, coming back to the topic of today's class, hydrologic modeling and remote sensing are very important tools for integrated urban water management. Right? By integrated management, I mean the rainwater management, wastewater management, and surface water, groundwater management all should be integrated. Right? And actually they are. I'm not going through the details of this cycle, but as you can see, the rainwater, wastewater, and surface water are actually very closely connected. Okay. So this is the chapter 1, and I have 2 recommended readings for you if you are interested, in this brief history or in urban hydrology. You may want to read more about it. Okay. So let's see what's the time now. It is 9:50. Oops, 9:49. Okay. So what's our schedule? What did I said? Well, obviously we are already behind the schedule, but I do want to take a very quick break, maybe 5 minutes. We can come back at 9:55. Especially if you have been following our summer school from day 1. I think a lot of things have been covered by different instructors. So I will try to go quickly here. So my goal for chapter 2 is not to introduce like the technical details of remote sensing or hydrologic principles, but to introduce you that how remote sensing can help with hydrologic principles. And also we need to understand those hydrologic principles in order to do hydrologic modeling in the next chapter. Okay. So coming back to this figure of hydrologic cycle, and a lot of those processes are actually quite important. So we basically have to understand each of them, right? So, and remote sensing, as you may have known, that this is the process of detecting and monitoring the physical characteristics of an area by measuring its reflected and emitted radiation at a distance. Okay. So as you can see from this figure, there are actually a lot of different technology in remote sensing. Right? So if we see from the distance above the surface, right? So near surface, we have radar, right? We have cell signals. We can even have like mobile, cars or like rovers, balloon, right? This is a little bit far from the surface. And then if we go further, we have airborne instruments. So there are like obviously satellites and so on, right? So all of those different remote sensing technology, again, I don't think I can cover all of them, but as you can see in the next uh, couple slides, that they have been all very helpful for understanding hydrology. Okay. So I'm going to introduce one by one, hopefully very quickly, regarding hydrologic principles, including precipitation, both rain and snow, evaporation and evapotranspiration, then stream flow, then watershed. Okay, so we will talk about how remote sensing can actually, be applied to each of these hydrologic principles. Okay. Precipitation. So first, we are not going to talk about the formation or the forecasting. That belongs to meteorology, right? So then also precipitation include different types, right? So rain, snow, hail, drizzle, sleet. So here we only focus on the two most common, rain and snow. So why we talk about precipitation first? Because this is the first input to any hydrologic studies, right? So if you don't know precipitation, there is basically no hydrologic studies, right? So this is an essential input to hydrologic studies. In hydrologic engineering, it is important for planning, for design, for operation. I will skip this. Also, we will briefly talk about the temporal and spatial variability and how remote sensing techniques can actually help to resolve some of that. Okay. So here, just to bring everyone on the same page, I know many of you may have seen this or have learned this before. So this is a rainfall hydrograph, right? So a rainfall hydrograph is a time series of rainfall intensity. Right? As you can see in the x-axis, this is time in hours. In the y-axis, it is rainfall intensity. Here is in the unit of inch per hour. It can be millimeter per hour. Right? And if you plot it, plot this time series, this is the hydrograph. Okay. So obviously, rainfall intensity is not uniform, right? So during one rainfall event, it goes up and down, up and down, up and down, right? So it is not a constant or uniform. So another way to represent rainfall is the cumulative mass curve, right? So again, here x-axis is the same, is time, but the y-axis, instead of rainfall intensity, this is the cumulative rainfall depth, right? So because it's cumulative, obviously it starts from 0 and goes until the end of this rainfall event. So events, okay. If you look at a long time series of rainfall records, okay. So here is the example of city of Buffalo in New York State, in the United States. In 1993, right? This is from January until December of 1993, and as you can see that. The rainfall intensity, right? So sometimes, okay, if you look at this as example, right? So this looks like one continuous rainfall event, right? Then there is a dry period, then another rainfall event, okay? But sometimes it won't be that clear, right? So for example, here, there is a dry period which is very short. So do we consider this as one event or two events, right? So this is a problem. For determining rainfall event, so we need a concept called inter-event time definition, IETD, or a minimum inter-event time, MIT. Okay. So this means if we consider these two events, right? So if the dry period B is larger than IETD, then they will be considered as two separate events, right? But if B is smaller than IETD, then here, for instance, right? So this dry period is smaller than IETD, then this will be considered as one event instead of two events. So we don't have much time to get into the details. There actually something pretty interesting about this definition, and I think a lot of research could be done. But for today, it's just a brief introduction. And after defining rainfall events, right? After determining these rainfall events, so the properties of rainfall events include the duration, intensity, of the average intensity, so the interstorm or inter-event period, and then also the within storm temporal patterns. Okay, so all of those are very important properties, and when they are different, so for different rainfall events, the hydrologic response can be pretty different, right? So for measuring precipitation, there are basically four types of measurement. One is rain gauges, right? So those are ground-based and direct measurement, but obviously, this is difficult to cover spatial density, right? So it has very limited spatial density. Then the next one, radar. So this is the indirect measurement. It still is limited coverage, so you cannot rely on one radar to cover all area, right? You have to install a system of radars to cover a large area. Right? So then there is satellite. Obviously, satellite has a larger spatial coverage than radar. But the problem or the drawback is it also becomes less accurate. Okay. Finally, the last one is not discussed much, but I want to introduce this pretty interesting technology based on wireless or cellular signals, but it is still under development. So the rain gauge, there are different types. I will go very quickly. Right? So the most simple one is the Siemens type rain gauge. This is a non-recording type. So basically a bottle receiver. Then after each rainfall event, somebody has to go and check and read this, right? And obviously, if the rainfall is more than the capacity of this, then you will not know the real rainfall depth, right? So then there are recording type rain gauges, such as the tipping bucket type, like this. So this tipping bucket, basically, every 1 inch, it will reset. Okay, so it goes from 0 to 1, then back to 0, 1, 0, 1. Okay, so all of these are recorded automatically. And the wing bucket type, then a floating type. Then the optical type actually use a similar technology, the same technology as remote sensing, right? Only thing is it's not quite remote, okay? But it is still based on the reflectivity. So those are the rain gauges. The radar, so based on the radar reflectivity Z, and then by developing a relationship between Z and R, the radar reflectivity and the rainfall rate, then by measuring reflectivity, we will know or we can estimate the rainfall intensity, right? So this is the radar. The challenges with radar or the problems with radar include first, this relationship actually varies with time, location, and season. So you have to be very careful developing this relationship, and it has to be flexible and calibrated. It also requires a good radar coverage, right? So for example, as you can see here, right? So if the rainfall is too far away from a radar, right, then this measurement is not going to be accurate. And also the reflectivity can be affected by different particles or different objects in the air, not only rainfall droplets, but if there is, for example, insect, right, that will affect reflectivity as well. So for satellite, I will just quickly skip this similar idea as radar, but obviously this is with a better spatial coverage, but as we have said, less accurate. So the interesting one is wireless or cellular communication networks. So basically based on the cell signal, right? So the cell signal is also affected by rainfall, right? And this effect could be translated or calculated for rainfall intensity. Okay. So the concept was kind of proposed and proved in 2006 and published in Science. As you can see, for this rain gauge, the comparison between the rain gauge, the cellular link, and the weather radar are pretty similar. And actually, for some of them, the cellular link is better, even better than radar, right? However, it is not very easy or convenient to adopt this technology. Then until 2013, so this is actually the first large-scale study using this approach. Right? So this paper published in PNAS. So they studied the entire Netherlands and used about 2,400 cellular links to estimate the precipitation or rainfall intensity. Okay. So for spatial variability, I think this is nothing new. Here is an example of the United States. As you can see, this is the annual precipitation normal, a 30-year normal from 1981 to 2010. So obviously, rainfall or precipitation is different at different location. Okay. I should point out not only in this such large scale. I don't know if you guys have experienced this even within a city. Let's say like from a kilometer away or 10 kilometer away, there can be rainfall at one place and nothing, no rainfall at the other place, right? So rainfall can have a very big spatial variability. So for dealing with the spatial variability, so we have to, based on, for example, if it's a measurement of rain gauges, right, we have to do an aerial precipitation based on the point measurement, right? So there are different ways to do that. Again, I will just skip this very quickly, right? So arithmetic mean testing polygon, which is probably the most widely used. Arithmetic mean is pretty simple, right? This is the simplest. This is maybe the most widely used. Isolator method is believed to be the most accurate, but it's not very widely used because it's not really convenient, right? So every time when the rainfall intensity or rainfall depth change, the isolator lines will change, right? So this is different from TSM polygon because TSM polygon only depends on the location of the measurement, right? But isolator, like this will depends on the measurement itself, right? So obviously the radar and satellite-based estimates will at least partly address this issue, right? Because those are not point measurement, right? So this has a spatial coverage. So their aerial precipitation will be different from the ground-based or the point measurement. Okay. So then for snow, well, about 1/3 of the Earth's land surface is seasonally covered by snow or ice, and about 10% of the land surface is permanently covered by snow or ice. Right. So here is a measurement. Again, this is based on remote sensing. Right? This is based on remote sensing measurement of the snow cover and land surface temperature. So if you don't have remote sensing, measuring snow can be difficult. Okay? This is not an easy job. So the manual measurement is to use snow courses. Right? So those are like a vertical marker that you can put through the snow and then measure snow depths, right, based on those markers. So obviously is not very accurate, right? Because the snow is spatially variable, right? So here you can only measure at one specific location, only very few data points per year, and not exact timing, and pretty dangerous. A lot of training, all of these problems. So a more advanced measurement technology is called the snow telemetry, right? So as you can see, a lot of sensors have been used for this. And also the airborne survey, right? So these can be used for measure snow. So if you are interested, there is a pretty good video by NASA. I talk about their snow observation project. And also satellites. So just to give one example, like NOAA has this national snow analysis based on satellite. And here is another example, using the MODIS satellite images to measure snow depths. Evaporation. Okay, so evaporation is the net process by which water changes from a liquid to a gas or vapor. I think most of you are very familiar with this now. One thing to point out that the phase changes involve heat exchange, right? So this is called latent heat, and obviously this need energy, right? So from water to gas or vapor, it will need energy, and from snow or ice to gas or vapor, it will need more energy. So the measurement of evaporation is to use pan. So as you may remember, like even the first measurement of the Mediterranean Sea evaporation is using pan, right? Or used pan. So there are different types of pan. So the class A land pan, this is sitting on top of the ground. Right. There is also a Colorado sunken pan, which the water level is kept at the same as the ground level, right? So this is digged into the soil, and then there is a floating pan that is in the middle of the open water, right? So because of the measurement technique, so the evaporation from a pan is going to be faster than the natural evaporation in open water. So therefore, you need a coefficient to correct this measurement, right? So this coefficient is less than 1, right? It's because the evaporation in a pan is faster, right? So this is more than reality or more than open water evaporation. So the coefficient can change from 0.7 to 0.8 as average. Right? Of course, there is a range. So we can also use remote sensing technology to estimate evaporation using the Penman equation. Okay, so this is Penman equation. Those are the measurement you need to estimate evaporation. Okay, so I'm going to skip this. And here is a results, right? Here is a calculated evaporation over the US, right? So this is uh, average in August from 1971 to 2000. This is millimeter per month of evaporation. Evapotranspiration, this is the loss of water from the soil both by evaporation and transpiration. Okay, so it's actually a combination of two processes, right? Evaporation and transpiration. Okay. So evapotranspiration, or ET, is quite important. It accounts for about 10 to 15% of the atmosphere's water vapor. And to provide ET also provides an accurate calculation of the amount of water needed for specific weather and a specific set of plants. Okay. However, it is pretty complex because it depends on different factors, right? Such as temperature, relative humidity, wind, soil moisture, and the type of plant. Okay. And measuring evapotranspiration is really not easy, right? So, just to give an example, there is actually no like standard equipment to measure this. So this measurement is called lessimeters, right? So basically based on a water balance calculation. So you measure rainfall, you measure soil storage, you measure runoff, then based on water balance, you calculate evapotranspiration. Right? However, thanks to the remote sensing technologies, there are actually a lot of remote sensing based evapotranspiration estimates. So I'm just giving examples here. The Landsat-based Google Earth Engine, MODIS-based, and there are also data from GLDS or NLDS for soil moisture and evapotranspiration. Okay. So potential evapotranspiration is an idea introduced in 1941 by Southwind and Holzman. So the idea is imagine if you have a sufficient water supply, if you have a sufficient supply of soil water, so the maximum evapotranspiration will be the potential evapotranspiration. And the idea is knowing hopefully, first, knowing potential evapotranspiration is easier than knowing the time varying actual evapotranspiration, right? And then you can try to develop a relationship between potential evapotranspiration and actual evapotranspiration. Then based on that, you can estimate the actual evapotranspiration, right? So this is the whole idea why this potential evapotranspiration is introduced. So the actual evapotranspiration, or AET, that can be a function of phi times PET, which is the potential evapotranspiration. Right? And this Fi is called as the soil moisture function because it mostly depends on the soil moisture, right? So this M is the soil volumetric moisture at 20 centimeter depth and divided by the field capacity. Okay, so this can be estimation or a formula to calculate actual evapotranspiration based on potential evapotranspiration. And here is a database, again, just as an example, that we have hourly potential evapotranspiration data globally from 1981 until present. So if you are interested, you may want to check out this paper. So this is at a 0.1 degree resolution for the global land surface. So stream flow measurement, as we have said, Henry Pitot so invented the Pitot tube for measuring flow velocity. Since then, we could have accurate flow measurement. So this Pitot tube is based on the Bernoulli's theory or Bernoulli equation. I'm going to skip this. There is a link here, goes to a YouTube video. If you are interested, you can look at the explanation of Bernoulli equation. When you measure stream flow in a river, right, have to keep in mind that you have to measure at different depths and different locations of the cross section. So that is because the water velocity is different from surface to the bottom and from the middle of the river to the bank of the river, right? So why they are different in this need hydraulics. So it will need more time to explain that, but just keep in mind because of this velocity distribution, right? In order to measure flow discharge from at a cross section, you actually have to measure different places, which is quite time consuming and difficult, right? So this is like the manual measurement. So the measurement equipment, right? This is commonly used by the USGS, US Geological Survey, which is called Price AA current meter. So basically has a wheel of 6 metal cups, then it automatically records how fast this actually it will time and count how many revolutions. Okay, so if you are interested, there is a link for more information. Then the acoustic Doppler flow meters are called acoustic Doppler current profiler, or ADCP. So this is based on the Doppler effect, right? Which is the sound waves bounced back from a particle moving away from the profiler have a slightly lower frequency when they return. Right? So by this, ADCP can actually measure area of a cross section simultaneously, right? Almost simultaneously. So you don't have to take measurement at each location. And by the way, keep in mind when you do it manually, you have to measure for a certain time period, right? Normally a couple minutes at least, in order to get the average flow velocity. So now you can get like a instantaneous measurement. Okay. Also very interesting is image-based stream flow measurement. So again, this large-scale particle image velocimetry, or LSPIV, is still under development, but it's quite interesting. Although the technique has been already widely used for a long time in the laboratory, right? So this is a typical PIV system at our university that you can measure flow velocity at a very fine resolution and very good accuracy in a lab scale, right? However, using a similar technique at a large scale, like this, like on the left, I think this is still a very interesting idea. Seems promising, but it is largely under development. So if you are interested, this is one example called the Pi Open River Cam. So you can see what people have been doing for this. Okay. So the watershed is basically all points enclosed within an area from which rain falling at these points will contribute water to the outlet. Right? So this is the idea of the Mississippi River watershed. Right? So why it's important? Because watershed is like normally used as a basic unit in most hydrologic analysis. Right? So watershed delineation is based on elevation data, right? So actually the DEMs, the digital elevation models, can be used to either manually or automatically delineate watersheds. So I think this might be very familiar to most of you. So the DEMs can come from topographic maps and or also from LiDAR, right? So this is an example of LiDAR. Um, so if you think about the important watershed parameters, the size, the slope, the shape. So once we have the delineated watershed and based on the elevation, it's actually pretty convenient to get those, right? The size, slope, and shape. Land cover, land use is also important for watershed. The soil property is important. Then the channel morphology is also important. Here is just showing an example for two similar area of watersheds, but different shapes, right? So obviously the elongated shape has a longer travel time, right? And this concentrated shape has a shorter travel time. So under the same rainfall event, this one, the peak discharge will come earlier, right? And also expected to be higher than this one, right? And also between the natural and the developed, the peak flow is expected to come earlier and higher, right? So land cover, land use obviously is also a big application of remote sensing. Right? So here I'm showing again just two examples. One is a satellite-based 100-meter resolution for impervious. This is given by USGS. This is something we did at our research group that you can actually use LiDAR data with 2.6-meter resolution, and as you can see, like this land cover land use classification, obviously the resolution is much better than this one, right? But again, this is just as an example to show how remote sensing can be applied for this kind of knowledge, right? Okay, so hopefully, let me see what time we are. 10:30. All right, so we think successfully come back to our planned schedule. So let's take a break of 10 minutes. Then we'll come back at 10:40. Okay. See, most people are still here. It's good. There's one question in chat asked by Amit Kumar. Thanks for the question. So how can we determine runoff by remote sensing? Okay, so hopefully that question will be answered in this coming chapter, that we can do it using hydrologic modeling or hydrologic analysis, right? So let's see. Okay, let's get started. So this chapter, by the original schedule, it will be 40 minutes, but I think it will maybe like be longer than that. So we will see. Okay. So chapter 3, urban hydrologic modeling, or SWIM. So SWIM will be the modeling package we use to introduce urban hydrologic modeling. I should clarify that SWIM is not the only modeling package, and there are other packages that are available. But SWIM is one of the most widely used urban hydrologic modeling package now. So talking about, before we go into modeling, I want to just very briefly remind everyone, like where we are or where we were in the early 1900s, right? So for hydraulics, Manning's formula was proposed about 1890. Then about early 1900s, the infiltration theory by Green and Amt 1911, Houghton's formula 1933, and then Sherman also proposed the unit hydrograph concept or unit hydrograph theory in 1932. So until 1930s or 1940s, finally, hydrology became a more quantitative field that people can actually start to compute, such as runoff, such as stream flow, right? So basically, the rainfall runoff calculation, we had these tools, we had the theories to do that. However, that's not enough for modeling, right? Especially what we call model now is referred to as computer modeling. So in order to have the first computer model, we have to wait until the first computer was invented, right? However, before that, there was very interesting computer numerical modeling concept proposed as early as 1922 by Lewis Fry Richardson. So he is British. So in his book, Weather Prediction by Numerical Process, so he proposed and also he tested his idea by attempting to compute for an 8-hour period long of weather calculation for the British, which finally took 6 weeks and failed. Okay. However, so the concept, this numerical process concept, is pretty similar to what we are doing nowadays. And this is probably one of the most crazy ideas I have heard that actually worked, of course, like later by a different technology, but it finally worked. However, back then, Richardson failed. And interestingly, in his book, he used the word computers. Okay. And at the time, computers refer to people who did computation. Okay? Definitely not the computer we mean right now. Right? And what he proposed that although his attempt failed, he believed that if we can build a forecast factory, right, and hire tens of thousands of people to perform calculation at the same time, he believed that this approach could work. Okay. So again, I think if you when you read the history of science, there are always surprising stories, and I hope this can be inspiring as well. So the computer theory did not come until 1930s, right? So obviously in 1920s, Richardson couldn't do like what we are doing now, right? Because even the computer theory came in 1930s independently by Alonzo Church and Alan Turing. Okay? So this is called the Church-Turing. This is, or more often referred to as the Turing machine. Okay? So Alan Turing and Alonzo Church were trying to answer a question that what mathematical functions are actually computable, right? And in order to answer this question, they actually built up the foundation of the modern computer theory. Of course, the first modern computer didn't come out until actually 1940s. Right? So in 1950, another important man, von Neumann, so his team performed the first numerical weather forecast on the ENIAC computer, right? So which is one of the earliest electronic general purpose computers, and finally proved that the concept by Richardson, 1922, actually could work, but not with human computers, but with electronic computers. Okay, so then later in 1960s, computers became more accessible to researchers, although it's still not that accessible to the public, but it at least became accessible to research institute or universities such as Stanford, right? So in 1960s, Crawford and Linsley developed the Stanford watershed model. So this is one of the earliest hydrologic models. And by the way, here I'm only focusing on this history, the development of hydrologic models in the United States. So they are actually, of course, like in Europe, in Asia, different countries, there are also development as well. So then later, there is the Soil Conservation Service, SCS. They developed a method called TR20, which later evolved into TR55. Then U.S. Army Corps of Engineers developed the model HEC. This is a family of models, and one of the family member, HEC HMS, is widely used for floodplain analysis. Then the US EPA lead this development of SWIM, which we will focus on today, that is designed for calculating urban runoff. So SWIM is short for Stormwater Management Model. So SWIM, this is a semi-distributed dynamic rainfall runoff simulation model. It can be used for single event or long-term simulation. So the first version was again developed in 1960s. So late 1960s, early 1970s. But since then, it has been evolved and improved a lot. So the most recent version is 5.2. And I believe the most recent update is actually 5.2.1, which was updated in this month, August 2022. So here is a graphical user interface of this model. So this is a modeling package, and if you are interested, you can go to this website. It's a very good user reference user menu, and then very good reference menu. So of course we don't have enough time to go over all details. So the modeled processes in SWIM include this, right? So it goes from precipitation. If it's rainfall, then it goes to surface runoff directly. If it's snow, there is a snow melt process. Then it goes to surface runoff. Then surface runoff gives overland flow. Then also evaporation, infiltration, groundwater, channel, routing, and so on. Okay, so today will only focus on three parts because I think the others are either like more water quality oriented or the LID control. We will talk more tomorrow, and yeah, the other processes I think are more straightforward. Okay, so let's look at how surface runoff was calculated. So first, subcatchment is represented in swim as a rectangular surface, which looks like this. There is a uniform width, uniform slope, okay? And then it drains to a single outlet channel. Okay? So this is one subcatchment in swim. So basically, the overland flow is generated by modeling the subcatchment as a nonlinear reservoir. So here, as you can see, the whole watershed is considered as this reservoir with storage. This is a depression storage. Then when it's higher than the depression storage, then it can start to generate runoff, right? And obviously the input is precipitation, then there can be evaporation loss. Then the runoff is actually calculated using Manning's equation, right? So here width, slope, and delta H, right? So the conceptual model in swim actually divides one subcatchment into three sub areas. So those are A1, which is a pervious area, A2, which is impervious area with depression storage. And there can also be impervious area without depression storage. Okay, so I should clarify, you don't have to have all of the three sub areas, right? So for example, one subcatchment can be 100% pervious or 100% impervious, right? Or even with separation of pervious and impervious, you can have two impervious areas with or without depression storage. You can also have only impervious area with depression storage, right? Or without depression storage. So there are different options there. So the runoff is solved individually for each sub area, then combined together for the entire subcatchment. So that's the original runoff calculation. So later in early 2000, Huber extended swim to allow overland flow to be rerouted. By rerouted, it means the runoff or overland flow from A1 can go to A2 before going to the inlet node of the pipe or channel. Or it can go to A3 before going to the inlet node. And also the overland flow from one subcatchment can first route into another subcatchment, then from another subcatchment, it goes to a node or channel, right? So that's what it means by rerouting or rerouted. Okay. So infiltration, as you can see here, that precipitation and evaporation we have talked about, right? So those can be measured and those can be input into the model, right? And the runoff can be calculated based on that. But one more thing we need to calculate is infiltration, right? So how much water can actually infiltrate. So that has to be modeled as well, right? So by the way, precipitation and infiltration are usually much larger than evaporation or evapotranspiration during rainfall events. Okay. So that's again, infiltration is very important for calculating runoff. So during rainfall event, you could neglect evapotranspiration, but you cannot neglect infiltration, right? So if you consider the rainfall intensity versus the potential infiltration rate, okay, so actually, if rainfall intensity is smaller or equal to the infiltration rate, then there is no overland flow, right, or no runoff, because all rainfall can infiltrate, right? So only if the rainfall intensity I is larger than the potential infiltration rate F, then the overland runoff or surface runoff can happen, right? So for calculating infiltration rate, we will introduce the two most widely used methods, right? One is Houghton, the other is Green-Abt. So Houghton's equation is the empirical formula. So basically, Houghton proposed that the infiltration capacity is actually follow the limiting curve, which basically decays exponentially from F0, which is the initial infiltration rate, to the FC, which is the equilibrium infiltration rate, right? And between F0 and FC, this is proposed as a exponential function of decay. Okay, so the function or formula looks like this, right? F equal to Fc plus F0 minus Fc times the exponential function, which decays. So basically, there are three parameters here, right? Fc, F0, and K. Right? So F0 is the initial infiltration capacity, Fc is the final capacity, and K is empirical constant. Okay. So this equation or this method has some assumptions. And one of the assumptions is it assumes I is larger than F, right? Or it assumes like this infiltration capacity decreases as a function of time, regardless of the actual amount of water available for infiltration. So in other words, it assumes that there is always water ponding on the surface of the soil. Okay, so this assumption can be corrected, or can be modified by considering an initial loss. So before applying Houghton's equation, you could first apply an initial loss. By initial loss, you basically take consideration of this, before or pre-ponding period, and then after that, you can apply Houghton, which is after ponding. Okay, so this is a big difference when you see Green-Abt. You will see that Green-Abt actually can deal with ponding by itself, right, without that correction or modification. So given that said, because so they are normally not like very detailed measurement of actual loss rate, and also the urban watershed have high imperviousness. So this empirical approach usually give quite satisfactory results, right? That's also why it is so commonly used. So there are some calculations you could do, for example, the cumulative infiltration volume that will be the integral of infiltration rate, capital F, right? That will be a function of this. Why we want this? Because again, when you compare to Green-Abt actually is a function for capital F instead of infiltration rate F. Okay. So for the three parameters, depends on different soil types. These three parameters will be different. So Ross in 1983 has summarized this and suggested those values for different soil types. However, in hydrologic modeling, keep in mind those are or could be considered as calibration parameters. What does it mean by calibration? We will introduce later. Okay, so Green-amped method is the other widely used method for infiltration. So different from Horton. Horton is an empirical approach. Green-amped is actually a physically based approach. It's based on the Darcy's law. Of course, it takes a lot of assumptions. And one of the biggest assumptions is that it assumes there is a wetting front, right? And above the wetting front, there is a perfectly saturated zone. And then below the wetting front, then there is just initial moisture, basically without any infiltration. Obviously, this is different from reality, right? So the actual infiltration, there is a saturated zone, but between saturated and not being affected, there are actually a large area of transmission zone, right? So as you can see, like those are not really clearly horizontal wetting front like this. However, based on this assumption, so green and amped could derive a formula for calculating infiltration rate. Okay. So for the time being, I think I will just simply introduce the idea. So basically, if you think about the water volume or the total infiltration in this in the soil, right? Capital F. So that's the difference between the saturated moisture minus the initial moisture, then times the depth of this. So basically, this is the wetting front, right? So theta S minus theta I can be noted as MD, right? So this is MD times L. And the infiltration rate or the rate, the velocity of the wetting front, right, depends on basically the infiltration rate, right? And here it's assumed that the infiltration rate can be calculated by Darcy's law, right, which is delta H over, so this is Ks times the difference in water head minus so basically the gradient of the water head, right? So then this becomes Ks times 1 minus phi over L, and then basically this became the Green-amped formula, right? So as you can see, Green-amped does not give infiltration rate or infiltration volume explicitly, but it actually gives a relationship between F and capital F. However, based on the relationship, it's not difficult to get either F or capital F. Okay. So one thing to note is this phi, which is the capillary section, should be a negative value. Okay. In some cases, you may find in literature or other resources that phi is given as a positive value. So in that case, you either have to change it to be negative, or you use plus instead of minus if phi is a positive value. Okay. So basically, the calculation of f, because phi is a negative value, MD is positive, F is positive, so this is a negative value. 1 minus negative value is larger than 1, right? So F should be always larger than Ks, right? And Ks is the hydraulic connectivity. So there are different infiltration scenarios when you apply Green-amped. So first case is if the rainfall intensity is even smaller or equal to hydraulic connectivity, obviously all of the rainfall can infiltrate, right? So infiltration rate simply equals to rainfall intensity, and there will be no runoff, right? And then when the rainfall intensity is larger than TS, larger than hydraulic conductivity, then so as you can see from the formula, if you calculate F based on this formula, when capital F is very small, close to zero, then F actually goes to infinity, right? So again, which means based on Green-Abt method or based on the assumptions in Green-Abt method, at the very beginning of the time, so there is always that the potential infiltration capacity can be larger than the rainfall intensity, right? So then F equals to I until it reaches what is called the pounding time. So then after the pounding time, it starts to follow this formula, right? So first is the horizontal line B, and then decay as curve C. So how do we determine pounding time here? So because we know at the pounding time, first F equal to I, and then F also equals to the Green-Abt formula, right? So then basically I equals to this. So then based on that, you can calculate F sub S, which is the volume of infiltration at the moment of surface saturation or at the moment of pounding. Then Tp equals to capital F sub S divided by rainfall intensity, right? So this is the pounding time. This is the volume of infiltration at pounding time. So again, if you go back to this, as you can imagine when you compare this with Houghton, right? So Houghton is always a decay function, right? So Houghton is always decay. Again, that is because in Houghton, it assumes that there's always pounding water, okay? But if you apply Green-Abt, actually, it will first need to reach the pounding time, then it follows a decay, right? So in Green-Abt, there are also three parameters, right? The same as Houghton. However, those parameters all have physical meanings. So theoretically, it can be determined from physical measurements. And those are all soil-related physical properties. Right? So actually, these can be directly measured. However, keep in mind, because Green-Abt method is derived based on those important assumptions. Okay? So directly measuring the parameters do not necessarily mean that your model will be perfect, right? So you could have perfect physical parameters by measurement, but those cannot guarantee that your model will be good as well. You know what I mean? Because there are assumptions in the model. So to find the parameters, there are different data sources. Here, only giving you like one example. Again, it's based on the work of Royce, 1983. So depending on the different soil type, I can have different values of the parameters. Okay. So if you look at Houghton and the Green-Abt side by side, one is empirical formula, the other one is physically based. One like the decay coefficient in Houghton is difficult to determine. Then Green-Abt, the parameters can be determined from directly measured soil parameters, but again, keep in mind those measurements, are subject to calibration. Okay. So then Houghton assumes pounding regardless of actual rainfall intensity, and Green-Abt allows for calculation of pounding time. Okay. Again, Houghton by a correction or modification it can address this assumption of pounding, at least to some extent. Okay, so by introducing initial loss. So the hydraulics in swim, well, if we want to go to the details, it will take a lot of time. So here, like you can check out this video for introduction of swim hydraulics. So basically, it's based on open channel hydraulics. Okay, so continuity and momentum equations. If you think about continuity equation, right, which looks like this, then the momentum equation looks like that. And for momentum equation, if we assume the channel is wide enough and there is no Q, which is like external source, then the momentum equation can be simplified like this, right? Although simplified, but it's still quite computationally expensive. So sometimes we do not solve all of the terms. If we solve all of the terms, that is called a dynamic wave method, right? And if we assume like it is a steady uniform, then it becomes the simple kinematic wave method, right? So for swim, there are actually three options in swim, right? So two of them are kinematic wave and dynamic wave. The third one is even simpler than kinematic wave. So it simply doesn't consider any routine. It just sums the instantaneous subcatchment runoff. That's it. Okay, so this is like purely steady for the whole system. Although kinematic wave, the method is assuming steady flow. However, in swim, because the input is time dependent, right? So even though you apply kinematic wave method, you still get a time dependent or somehow unsteady flow results, right? Okay. So in a quick summary, there are about 20 parameters for each subcatchment in a swim model, right? You don't have to read into every single one, but those are a lot of parameters. Many of them are not very sensitive, but some of them are quite quite sensitive. So we have to pay attention to the parameters and the calibration and validation of the model. So by model calibration and validation, I mean, calibration is the process of adjusting model parameters and then comparing the model output to measured data until it reaches a satisfactory or acceptable level. Okay. So a pre-step of calibration is normally sensitivity analysis. That is the process of determining which parameters are more sensitive, right? Because it can save us time that we don't have to waste our time on calibrating some parameters that are not sensitive, right? So after calibration, we also need to validate the model. So the model validation is a process to evaluate the accuracy, uncertainty, and bias in calibrated model predictions. So again, today we do not have too much time to go through all of these details here. So actually, there are a lot to talk about model calibration and validation. So in the next chapter, I'm going to again only touch the surface of this topic. But again, because there are so many parameters in swim, and there can be also many subcatchments in swim, right? So calibrating such a model is not an easy task. Okay, And for validation, I want to mention one thing more thing that although model calibration and validation are still a very widely accepted best of practice for hydrological model development. Given that said, there are ongoing debate or argument regarding the the purpose or the necessity of validation. So if you are interested, there are very recent research talking about whether or not we need a model validation process. Okay, so I believe this should be chapter 3. Let me see what's the time now. I think we are pretty good, right? Yeah, actually we are. Good. We are even 3 minutes ahead of time. Yeah, I was a little worried that this chapter might take too long, so I probably went a little bit too fast. So if you have any questions, you can type in chat, and I will try to answer those questions. Otherwise, let's take a break, and we will continue to the last chapter at 11:25. Okay. So I saw the follow-up question by Shortcut Alicia, but I think we need to continue to the next chapter. Hopefully after that, I may be able to answer those follow-up questions. So in the last chapter, I'd like to show you some example and application of SWIM. Right? So we have talked about the theories, those processes, formulas. So what can we do with this model, right? So unfortunately, if it's an in-person training, we might be able to do some hands-on practice. But because now it's online, so I think I'm going to show you the example, and obviously the best way to really learn this is actually by doing it by yourself, right? So I will also upload some instructions as an exercise to your online learning platform. So if you are interested, you may want to follow those instructions and do this practice by yourself. Okay. So first, I'm going to introduce you an example from the swim tutorial. This is a pretty simple example with 3 subcatchments, 4 junctions, 1 outfall, and 4 conduits. Okay, so this is just for you to get somehow familiar with how a swim model looks like. Okay, so basically there are those like 3 main components. One is hydrology, right? One is hydraulics, then one is water quality. So here, today we are not going to focus on water quality, but mainly hydrology and hydraulics, right? So there are also others like options, climatology, curves, time series, time patterns, map labels. So I think later I'm going to show you the graphical user interface so you can get some idea. So the main components here, at least for this example, are subcatchment, right? So those are subcatchment. Rain gauge, right? You have to provide precipitation data, right? Either rain or snow, right? So there has to be a precipitation data as an input. Then for for node, it can be junctions like those, like J1, J2, J3, J4. It can be outfalls like this. So this is the final outfall. Then for the links, there can be conduits and there also can be outlets. Okay, so those are the different components. So if you follow the tutorial steps, again, unfortunately, we are not going to do it step by step together. Okay, but the steps are as follows, right? First, you need to build a new project. Then you need to set the default values. Then set the map display, set background pictures. Those are optional. Okay, so of course, build a new project is mandatory. Set defaults are also optional, but highly recommended. Set map display and the background picture are optional, so you don't need to do it all the time, but they can be helpful. So here, if you follow that tutorial, it gives you the parameters for each subcatchment, for each node or conduit. Right? So you just have to follow this step by step. Okay. So for the rain gauge, I think it's pretty straightforward. You need a time series for the rainfall hydrograph. Right? So remember what a rainfall hydrograph is. That's the time series of rainfall intensity. Right? So this can be a time series. So the data actually can be manually input, can also be input as a file. Right? So then for the subcatchment, those are pretty straightforward, right? So I'm going to skip this. Just keep in mind that infiltration, right? You have to select which method you want to use for infiltration. Right here, we select the green empt. Other parameters like the area, the width, the slope, percent of imperviousness, Manning's roughness for impervious area, Manning's roughness for pervious area, dispersion storage for impervious area, dispersion storage for pervious area, right, and so on. Okay, so those are different parameters or different settings. So for the node, first is junction, and then there can be also outfall, right? So here, imagine like this is a junction, right? So between two junctions, there can be a pipe or conduit connecting the two junctions. I think all the others are pretty straightforward. The only one I want to explain a little bit more is what's called ponded area, because this may not be so straightforward to understand. So what does it mean by ponded area? Ponded area means, imagine this is a manhole. Okay? In this manhole, so obviously the storm runoff can get into the drainage system from this manhole. However, if there is too much storm runoff coming in, right, so there could be ponding water on street, right? And if there are too much ponding water, that can be a street flooding, right? So, however, there is an option in swim model to either select ponding off or on. Okay, so if you select ponding off, that means all of the excess inflow to this node is lost from the system. So basically, you do not consider any ponding at this junction, okay, or at this manhole. It could make sense sometimes if imagine your junction may actually be close to some surface storage, right? So if there is ponding water, actually it will go to the surface storage and it will not come back to the drainage system. So in that case, this option will make more sense, right? It's more reasonable to select ponding off. However, there are other cases that you should consider ponding, especially if you are starting street flooding, right? So have to consider ponding on. And if you select the ponding on option, then this excess inflow will pond at the top of this junction or the node, and then later it will re-enter the drainage system when the outflow capacity becomes available. So obviously you can give the surface area for the ponding water. Okay, so the area does not have to be just the area of the junction, right? Because normally the area of the junction is very small, right? That's if an area of the manhole, like that is normally very small. But the ponding water actually can be distributed on a much larger area. So that will become another parameter to consider. Okay. So for the link or conduit, so you need to specify the shape of the conduit, the depth of the conduit, and the roughness of the conduit. I think all of those are pretty straightforward. So for roughness, maybe this is normally important calibration parameter because roughness controls the routing process, right? So roughness is pretty sensitive. And okay, coming back to subcatchment, you need to assign a rain gauge to a subcatchment and also assign outlet to a subcatchment. And then back to the junctions, you need to give invert elevation for each junction. Okay, so those are also actually straightforward if you follow the tutorial. Okay. So for the options, you select infiltration model, routing model, we have introduced those, whether or not allow ponding, right, and so on. Okay, so then you can run the model, right? So let me bring up the swim model, this simple example that I have already built. Okay. So as you can see, first, this is the graphical user interface of Swim, right? So you have the toolbox, the menu, and then in the project, there are different options, right? So those are options, climatology, hydrology. Then there is a rain gauge, subcatchment, and so on, right? Then hydraulics, so quality, curves, time series, right? So this time series is for the rainfall, right? So if you go to the rain gauge, we make it larger, right? As you can see, the data source you can select from time series, or it can come from a file, right? And if you select time series, you need to tell like which time series it is, right? And also the unit, is that in inch or in millimeter, you can select. So this is for the rain gauge. For subcatchment, as you can see, those are the parameters of each subcatchment. So each subcatchment, the runoff need to be discharged to outlet, right? By outlet, I mean the outlet of the subcatchment. So in this case, it's a junction, right? So this is a junction that will receive outflow from this subcatchment. Same for here, right? This is a junction receiving flow outflow from this subcatchment. This receive outflow from this subcatchment. And then those junctions are connected by pipelines, right? And finally, it goes to outflow. Okay. So you can run the model. Obviously, this is very fast because it's very simple. Right? Again, only 3 subcatchments, like 4 junctions. This is a very simple model. And we also run it for only one rainfall event, right? It's a very short event. So there are a lot of different ways to actually visualize your results, right? So normally I would start with the report, right? So if you go to the summary report, this gives you a summary of total precipitation, total runoff, total evaporation, infiltration, runoff, and so on for each subcatchment, right? So you can also go to different node, different conduit, right? So this gives you a summary. Of course, this is the summary of the whole simulation period. Okay? If you want to get a time series, right? So here you can do time series plot for different options. For example, we can add subcatchment, say runoff, right? We go to subcatchment 1. I hope this is called subcatchment 1. Okay, S1. Right. So this plot the runoff from subcatchment 1, and we also include the water depths at the outlet. Right? So you can actually include multiple curves in the same plot. Okay? So this is for time series. Another useful way to visualize the results would be to do a profile plot. Right? So let's start with junction 1, goes to the outfall, and find the path, right? C1, C2, C4. Okay. So this gives you from junction 1 until the outfall. Right? So if you go to map, and this actually can play a video showing you at a different time how the water level changes in each conduit and also at each junction. Okay. So you may notice one thing that let's go back to the beginning. You may notice one thing that all the time at each junction or at each conduit, the water depth is actually uniform unless it becomes pressurized, right? So if it's unpressurized, as you can see, this water depth is always uniform in each conduit. Okay, so that indicates that you are adopting a kinematic wave method for the hydraulics, right? So what if we do what if we do a dynamic wave? Oh, actually, that may already be a dynamic. Let me see if we do a kinematic wave method. Okay. So you can see when you do kinematic wave method at all the time, this water depth is actually uniform in each conduit, and at a certain time, it actually overflowed at this junction, junction 2, right? So that is giving by the kinematic wave method. However, if you select dynamic wave method, if you select wave method, then when it become pressurized, so it can actually resolve the water depth variation within each conduit, right? So in that case, actually, you see junction 2 actually will not be flooded. Okay, so that node flooding given by kinematic wave could be false, right? So this is the difference between kinematic wave and dynamic wave. There's also a difference if you want to try that allow pounding or not allow pounding, right? So in this case, because if we use dynamic wave, there is no node flooding, so then the pounding doesn't matter, right? But if you select kinematic wave, allow pounding or not allowing pounding, that will make a difference. Okay, so that's something you can say. That's for the visualization of this. Okay, let's go back to, all right. So here in this example, we do not do any calibration or validation, right? So this is just a simple exercise to build a simple swim model and then run the model. Oh, by the way, I forgot one thing quickly. That this simple example, actually, if you go to tutorial, you go to basic tutorial. So this is actually the tutorial, you could follow, right? So as you can see, like following this, you will get a model like this, right? So here are the different ways to check results, right? The status report, the summary report, result on the map, time series plot, profile plot. So I think we have shown everything except the result on the map. Okay, but again, I think we can skip it for now. So it's actually pretty straightforward if you explore this a little bit. So there can also be water quality simulated using Swim. So however, the water quality module is still quite simple in a way that also indicates that our modeling capacity for urban hydrologic water quality, I think there are still a lot of improvements to be done, like both the understanding and also like how to model it correctly. So in Swim, how it does the water quality modeling is by basically two processes. One is called build up and one is called wash off. So the build up process is under the dry weather. So it simulates the build up of pollutant on the surface, right? So these are modeled as different empirical formulas, like power function, exponential function, and so on. Okay, so as you can see here on the lower left lower left here, right? There are different functions you can use, right? Power, exponential, saturation, external time series. Then for wash off, similarly, there are empirical formulas. So these include exponential, rating curve, or event mean concentration, EMC. So if you follow the tutorial that you can see how the water quality here simulated as the TSS, total suspended solids. Okay, so that is a simple example, right? Here, there are a lot of applications of swim models. I think if you do a literature research, do a literature review, like you will find thousands of different applications. So here I'm showing you like something we did recently that is a small subcatchment within the city of Buffalo. So that include about 70 subcatchments, 75 junctions, 76 conduits. So obviously, for this more realistic model, we need to spend a lot of time and efforts on model calibration validation. So here we summarized like all the sensitive parameters uh, people have people have found in literature, and then based on that, we did our own sensitivity analysis and find out which parameters are the most sensitive in our case study. Then by calibrating the parameters, this is just to show you that the comparison between the simulation and the measurement, right? So here on the top is the rainfall hydrograph, right? And then on the lower part, this is the flow time series from 2016 to 2017. Right? So we pick these 6 months, about half year for model calibration, and then the second half year for model validation. Okay. So as you can see, the model actually can predict those events pretty well. For the peak events, there is a relatively larger difference, but again, those comparison are pretty good. Okay. So that is simple, like the tutorial for swim, and also I showed you just one application that you can do. So there are other works we did for analyze the climate change effects, also analyzing how to manage the system in order to mitigate command sewer overflows and so on. So tomorrow I will talk a little bit more about the second part, but I think that's pretty much it for today. Okay. So let me see. I think I may have some time to answer questions. I will start with the last one from Amit Kumar. What was the meaning of green line in this model? Wasn't sure what you mean by the green line. Are you talking about this line? Yes. Or maybe not. This line. Okay, so this is the gradient line, like, but in this case, it's simply just the elevation, the connecting of the elevation of the junctions. However, if the junction get ponding water or overland flow, these might be different. Okay, so let me see. There are some follow-up questions by Shukat Alisha. So can we use HCP or current meter for overland runoff? That would be tough because the main difficulty of overland runoff is these happen at a very shallow water depth, right? So the HCP equipment, it has to go underwater, and the size of the HCP or even the current meter, I don't think it will be good for overland runoff. So yeah, I guess that is the question, right? Okay, I think if there's no more question, we can end up here for this morning's session. And I would only just remind you that the summer school continues, right? So later in the afternoon, there will be another instructor talking about the topic of, let me open this schedule. So Professor Wang will talk about hydrometeorological monitoring, remote sensing application in real-time precipitation monitoring. And then tomorrow at the same time,